Okay, I'll try to be very brief, so I'll try to just make, to remind you some basic thing, and I hope it will be not very long, and we will switch to Kolmogorov complexity soon. So Shannon entropy is defined for random variables, and random variables mean that we have some alphabet, sigma, and we have some letters, which have frequencies P1, Pn, and the sum of letters, sum of probabilities, is 1. And we want to define the Shannon entropy of this distribution. So we have a distribution, probability distribution, a finite set of finite alphabet, and so let me just start with a, I'll try to say it's, as usually people say, give a formal definition, 1 over pi. This is what is called Shannon entropy. And now still I want to explain how we get this formula, why it is, and what is this. So the idea is that we consider the idea of a code. A code is, if we have n letters, code consists of n bit strings. And we want the code to be uniquely decodable, or even better, should be prefix-free code. None of the words should be a prefix of another word. And this makes some requirement to the length of the strings. And the requirement, as we have proved, or at least shown yesterday, is that the sum of 2 to the minus li is less than 1. Each of the words somehow cuts a piece in the space, and so it's necessary and sufficient conditions for the existence of prefix-free code with given length. So this was the lemma we proved yesterday. And also there is a statement, more general statement. It's actually true for also necessary and sufficient conditions for uniquely decodable codes. But it's more difficult to, it's a very nice, funny proof, but since you want me to be short, it's probably we should skip it. But this is called, for prefix-free code, it's Kraft lemma, and for the uniquely decodable, I think it's called Macmillan equality. Okay, and then the optimization problem which we tried to consider is just given P1, Pn, find the strings W1, Wn, which are prefix free, and make the average length of a number of bits, average number of bits per letter used in the encoding is should be minimal. It's an average length, how many bits we need in average per one letter. So this is the main problem, optimization problem, when we have given frequencies and want to find strings. Okay, so let's stop at this point. Is it clear what is this problem, and why do we want this, or something like this? Or are there any questions? This is the most important place. So who thinks that he or she understands the setting and what we are looking for and what is happening? Okay, I can. So now, first, what we do, actually, due to Kraft lemma, we can reformulate this formula, this combinatorial problem. We want to find, actually, we need to find the length of the strings. After we find the length of the strings, we find the strings themselves using this Kraft lemma. So find the strings, integers, such that the sum of a 2 to the minus li is less than 1. And under this condition, we want to make pi li minimal. So this condition, this inequality for probability doesn't allow us to make li small, but still very small. But still we want to make this weighted sum of them very small. So this is our task. And now let me tell you general picture. So first of this problem, this optimization problem can be solved exactly, and we can find this optimal code, and maybe you know how it's called. It's Huffman code, and there is an algorithm how to construct this code. Actually, you need to take two letters which are most rare, combine into one letter, construct recursively the code for the alphabet with without the number of letters which is one smaller, and then if you find the code for this combined letter, then you need to split this code into new code words, just adding 0 and 1, and it's also prefix code, of course. So this is a Huffman code, and you can prove that this is an exactly optimal code, so we can solve this problem exactly. But actually, it's not what Shannon entropy is about. And Shannon entropy is about the relaxation of this problem. Imagine that we don't require them to be integers. So it's a kind of stupid idea to somehow corresponds to codes which have 2.5 letters or something like this. But still this thing has a clear meaning. And so we can look for the optimal solution for this relaxed problem, and then try to compare how much do we lose if we switch to integer values. And what is the solution for the relaxed problem is exactly what is the Shannon entropy. And this is what we should see now. So it's better to consider to rewrite this in other variables. Let's introduce new variables qi, which are just the 2 to the minus li. So in these new variables, we know that just the sum of all qi is at most 1, and we need the sum of pi but times log of 1 over qi. We should make it minimal. So now they are real variables. So actually, of course, we can even assume that the sum is equal to 1, because if we make them bigger, things are even better. The 1 over qi is smaller, and logarithm is smaller, so it's better. So we just have kind of, so we have the simplex in the space of q's. And we should minimize this function on this simplex. So how actually, when we go to the boundary of the simplex, the function becomes infinite, because then if some qi is small, then logarithm is very large. So there is a minimal somewhere inside. And how to find the minimal of a function of a, so what should we do? What should we differentiate? How you in mathematical analysis courses tell you what to do. So who can tell the answer? Yeah. Sorry? Oh, yeah. It's very serious thing, but we can say even easier. We can consider this a function of qi's, and then we can find this is a function. We can take a gradient, a vector of partial derivatives, and what it should be. No, because we have kind of restricted optimization. We optimize this on this special hyperplane. So if we have a maximal point, what it should be? Yeah, so the gradient vector should be orthogonal to the hyperplane. And the orthogonal vector is just vector 1, 1, 1. So all the derivatives according to, with respect to all the variables should be the same, which means that pi, and this is just derivative of this, it's minus pi, no, it's minus log qi, so it's just py, should be the same for all I, which means that P should be proportional to Q. And so so since the sums are 1, so actually Pi is equal to Qi. So this is the minimum point. So now we can say, summarize what we say. This is Shannon theorem. First part is that any prefix-free code for probabilities P1, Pn has average length at least this Shannon entropy of P1, Pn. If you remember that this is sum over Pi 1 over log 1 over Pi. So this is because this is absolute minimum for even if we relax our problem, we get this minimum, and so without relaxation it may be greater. And this is in one direction, and then we want to prove that, say something in another direction. There exists a prefix-free code of average length at most something. So what will be the bound? Who can say what is the bound then? Yeah, actually the answer is the Shannon entropy plus 1. So the idea is that relaxation costs at most 1. Because why it costs only 1? Because imagine we have found our optimal code, our optimal Li without integrality requirement are just log of 1 over Pi. And then we need to increase them to make them integer. So if we take the integer which is above them, we increase this thing at most by 1. And so if we average the things, the average also increases at most by 1. So this is the Shannon theorem. And that's a good point to stop a bit. And so is it clear, or are there any questions how it's proved? Okay, so who thinks that it's clear? Please raise your hand. Okay, but let me ask, are there any people who didn't know it before, but now think it's clear? It's okay, it's less convincing result, I should say, but okay. Actually, you can, if you don't want this relaxation story, you can say that there is a kind of, this part can be proved. It's Jensen inequality, and the logarithm function is convex. So the important thing that if we take a logarithm function and we take a straight line between 2 points, it's below the graph. Actually, you can use this property to prove it formally without all this gradient things and so on. But anyway, this is a Shannon theorem. Okay, so let's see some how it can be used and what it gives in some special cases. For example, let's prove that entropy of any variable which has n values is at most log n. So why if we have a variable with only n values, then its entropy cannot be very large. It's at most log n. Actually, log n will happen if all pi's are equal to 1/nth. Then all the log 1 over pi will be n, log n. So we get this log n average. And this is the maximal possible entropy for the. So if you want to create a maximally unclear outcome of some experiment, you should consider n equal probability outcomes, and outcomes of equal probabilities. So, but how do you prove this? Can somebody explain? No. It should be one. The proof should be one sentence without any formulas, just a simple sentence. Yeah?
You just maximize the sum of two logarithms, and you have the constraint that the sum of the arguments is the same. It means
No. It's too long already. Just one simple sentence. Does anybody seize? So remember that entropy is an optimization. It's a minimum of some optimization problem. So, and we want to show that this minimum is smaller than log n. Yeah. So what do we do?
Surely we have a code with
So we can consider a code which assumes that all things are equiprobable. Qi is 1 over n for all n. And this code will give the average length pi log n, and which is of course log n. So if we use this standard code, as every letter will have the same probability, and compare our optimal code with this code, then of course our optimal code is better.
This doesn't work. You have to round up.
Sorry?
But you have to round up the length of the words.
No, in the entropy, we consider the relaxed problem.
Yeah, but you refer to the code.
Okay, when I say code, you should understand this code in quotes. So it's a relaxed code. So we just consider the optimal of some problem. And if we find some solution for this problem, an optimal solution will be smaller. So we don't need actually code words. We just consider optimization problem and compare the minimum for some point which we can find. Okay, so then there is another thing which is called, okay, let me say just one more thing about Shannon entropy, and we switch to Kolmogorov complexity. So imagine we have two variables, psi, which has some probabilities p1, pn, and some other variable, for example, eta, which has probabilities q1, qm. But imagine that they are not just two different variables, but they have some common distribution. So we make some experiment, in which experiment we have one value of xi and one value of eta. So there is some probability, I don't know, Rij is a probability that xi is equal to I and eta is equal to j. So we have kind of table, but here we have xi and here we have eta. Here we have n values and here we have m values, and there is Rij. And so what is the relation between R's and P and Q? How you say this? So to get P, we should sum over, for given value of xi, we should sum over all possible values of oops. So the sum should be here, should be Pi. And the sum here should be Qj. And they are called, in probability theory, they are called marginal distributions. So then we can consider entropy of each variable, psi eta, and also the entropy of pair. And there is an inequality. So the entropy of the pair is at most the sum of the entropies. Why it's so? You can also prove it in one line, in one sentence, without any computation. No, maybe some computation still you need to have in mind some computation. But usually if you don't think about this as optimization problem, usually you just need to write some formulas and use some inequality and so on. But in optimization terms, it's easy to say. How will you do this? Yeah?
So maybe again, as the previous, we show that this is not a bound. So we can achieve this bound by just using probabilities fixing C and writing over A.
So we need some encoding for, let's speak about encoding and forget about this rounding problem. So we need an encoding for pair. And to show that the entropy is less than this sum, we should need to provide some encoding which will guarantee this kind of thing. So what is encoding you will use? So you find that you take the optimal encoding for psi, and optimal encoding for eta, and then just now, of course, it has no meaning because it's non-integer things and non-existing things. But you can take a code for psi, optimal code for psi, optimal code for eta, and concatenate them. And actually, if you have two prefix-free codes, you can, if you concatenate them, you get a prefix-free code because first you read things from left to right, and then you see when the first code word stops, and then you see when the second code word stops. But of course, we don't have this real codes, so we should say that let's use some qij for pair of values ij equal to what? No, if we speak in terms of probabilities, exponential scale, then it will be not the sum but the product. We take the product. Oh no, q is not good because q are used. So Sij product, it will be pi qj. So we use encoding which doesn't take into account the fact of dependence. Maybe it's not an optimal encoding, but still it's summed. So the entropy of the pair is bounded by the average code length for this encoding. And this average code length is the sum of Rij log 1 over pi qj, which is actually, this is equal to log of 1 over pi plus log of 1 of qj. And if we just, now to make the sum, there is, this part depends only on I, and this depends only on j. So actually it's just easy to see that it's just sum of entropies. Okay, so this is okay, let me just say still one more thing, which is called conditional entropy. So imagine somehow it's the amount of information psi if eta is known. It's a kind of thing which one should be accustomed to. Actually, we can again define it very formally, just as the difference between in this inequality. It's just the if they are, if actually the things are this inequality when psi and eta are independent. And the measure of dependency is just the difference between this. But we can define the conditional entropy like this. And it somehow corresponds to the following idea. So there is some message, for example, eta, which is transmitted. Okay, let's make a picture smaller. So imagine that there is some place when there is message eta, and then this message is transmitted to the, so it's send a receiver of our information, and the message eta is transmitted anyway. So for example, eta is somehow, I don't know, the television information, just or some newspaper or whatever. And there is some kind of other information, psi, which is, for example, the real information, not the newspaper one. And they are somehow dependent. They don't coincide, but they are dependent. And the goal is, we know that our correspondent, we want to send to some person, we want to send the real information. But we know that he will get the newspaper anyway for free. And so our question is that we need to send some additional bit string, which will strings which after this we can reconstruct psi. And this additional, how long this bit string should be in average, this is just this conditional entropy. So this is something in Shannon information theory, and yeah. So this is probably so independent psi and eta means that knowing eta. So having a newspaper doesn't help us. The fact that somebody gets the newspaper doesn't help us at all. So if this is the same as the entropy of psi, then we say that they are independent. It's equivalent to this thing. And also it's equivalent to, we can prove that this is equivalent that sum of eta and psi and eta is the sum of the pair. Okay, so this is the short reminder on Shannon entropy theory, and there is also some kind of Shannon coding theorem, but maybe we will after we learn something about Kolmogorov complexity, maybe it will be easier to consider it. Okay, so any questions up to the moment? Okay, so let me then we can completely switch to other topic for a while, and which is Kolmogorov complexity. So if you want to say in one sentence what is Kolmogorov complexity, it's a kind of compressed size, but with some important corrections. It's somehow a compressor size without compressor, actually. So what we are interested is we don't worry how we compress the string. We want only to be able to decompress it. So the formal definition is like this: first let D be any function, partial, from bit strings to bit strings. I don't know how to denote them, just like this. And then the informal idea that D is a decompressor. We get some string which is assumed to be a compressed description of some other string, and then we apply D and we get this other string. But just let D be any function. And then we define complexity of a string X according to this decompressor D as what? How will you define it? its minimal length of a string p such that d of p is x. So can be just so p. We can say that p is a description of x if d of p is x. Then we can say that the Kolmogorov complexity of x is a minimal description, length of the minimal description, and d is a kind of a description mode or decompressor or whatever. So, but formally it's just a strange formal definition, which at first has no sense, but still let me just to check that we understand it formally in the same way. Imagine that d of x is x. So what is Kolmogorov complexity given d? Let's see, d of p is p. It's better to use the notation. So kd of x is then what? Length of x. Okay. And imagine that d of p, I don't know, is 0p. Then kd of x is what?
X starts with 0.
Yeah, if x starts with 0, then it's what? Length of x minus 1. And if x starts with 1, that's infinite. That's a minimum of an empty set, and all mathematicians know that this minimum is infinity. There is a very good test to check whether a person is a mathematician. You look at a text editor and ask the person what should the text editor do if you want to push the button which says that put the marker in the first symbol of the line. So if the line has some letters, there is a special button which it's called, I don't know, line. Well, there is some special button for this, which puts us on the first letter on this line. And so the question to distinguish mathematicians and normal people is what the editor should do if the line is empty, and you still push the button, put on the first symbol of the line. So a mathematician will clearly see that it should go to the end of the line, and normal people usually say that it should be the beginning of the line. But so it's a kind of test. Okay. Okay, if we see, okay, let me just consider one more simple example. Imagine of d of p is just the two copies of p. Then kd of x will be what? Just say the answer. What will be complexity according to this strange decompressor? It will be if x is a copy y for some y, then it will be what? Half of the length. And if it will be infinity, if x is not of this form. Okay, so you see it's stupid questions, but still just for training, let us consider two other questions. But first let's give a definition. So of course we want our decompressor to be good. And good means that it provides short descriptions. So we say if D1 is better or not worse than D2, if what will be the reasonable definition? KD1 is for x is what? It doesn't exceed KD2 or for every x. This will be a most natural and good thing. But to get a reasonable theory, we should relax our requirement a bit and allow things to be just a bit worse. A bit worse is asymptotically constant. So we should say that for some constant, there exists some constant which, and K1 can exceed K2 at most by this constant C. So if we just constant overhead we ignore. And now the question, imagine we have two decompressors. And we want to find one which is better than both. How do we do this? So we want some just quite natural thing. We have some decompressors. One of them is good for one type of files, and another is good for other type of files. And we want to construct something which is as good or better, not worse, than both of them for both type of files. So what do we do? Sorry? In parallel, but we make some decision. Should make some decision. No, the minimal one. No, the compressor get a compressed. The compressor get a compressed string, and it doesn't have the original string. So we cannot say that around the D1 if depending on whether which is better.
We should put the number of the encoding function.
Yeah. So we need to add an additional bit which will say which decompressor is better. So we say D of 0x is D1, or maybe it will be better to say D0 and D1, okay. And not x, but p. And D of 1p should be D2 of p. Yeah. So our decompressor should allow both encodings, and the first bit is used then to select which one is used. And this D is better than D1 and D2 with which constant? But of course 1. The constant is 1 because we just lost one bit for these things. And if you, I don't know whether some of you have learned the internal structure of standard compression program like zip. But if you look at zip format, it's just made like this. There is first some header which says which decompression algorithm you should use. And then the decompressor unzip looks at this and select what to do later and applies one of the decompression methods. So it's not so. No, I wouldn't say that this Kolmogorov complexity theory made this possible, but actually it's a very natural thing which is normally done. Okay, and another question. Imagine we have some kind k different decompressor and construct D which is better than all of them. So what will be the constant? What price we should pay for this? Yeah, we should allocate first log k bits for this selection, and then use one of them which is according. And now we are completely ready to a trivial but fundamental theorem, which is called Kolmogorov-Solomonov theorem, because of course everybody can prove it if knowing the formulation, but they just understand this idea. So let's consider only computable. So starting from now, we consider not any functions, but computable decompressors. And then there exists an optimal D, such that for any other D prime. So let's write that they are computable. D is better than D prime, which means that there exists a C such that for all x, k d of x is at most k d prime of x. Oops, interesting thing. Plus C. So this means this stands for this. Okay, so probably you see why it's true, and what will be this optimal decompressor. What should we do? So this optimal decompressor, D, what it should do, looking at some string. No, why should we speak about number? He just looks at the string and finds some prefix, which is a program in some language which we fix. Let's fix some language, universal programming language, which is self-delimited, so we know where the program ends. Like in Pascal, we have a dot at the end, or something like this. So, so looking at the string, input string P, we find a program at the beginning. And what we do then, and program, and the rest is some data, and then the decompressor should run this program on this data. So in this way, we can simulate any decompressor, and the price for this is just the length of the program. So let D prime be any other, and let P program is a program for D prime. And then we can say that KD prime of X, no, KD of X, is bounded by KD prime of X plus length of this program for every X. Because if there is a shorter code for X according to this program, then we can just append, not prepend this code by the program and get a string which will give the same result with a universal decompressor. Okay, so it's
But this decompressor, the D of D, should contain the information about the infinite number of programming languages.
No, we fix some programming language. We don't need any programming language. Just fix some universal programming language, whatever it is. It's important that we are able to write a program for D prime in this language. But there is no need to apply any programming language. Or I am answering the wrong question. No, of course you can have, though it's kind of standard trade-off. We can, informally speaking, if we use very specialized decompressor, which is good for some very special types of file, then of course, if we switch to optimal decompressor, we will need a long program, and this constant can be large. But this is unavoidable, because if it's very specialized, then some specific string could have a short description, and we cannot avoid this.
And do we assume that D is defined on each X?
No, in our definitions, the decompressors are partial.
But then we can, for some X, there can be, it can be undefined.
Okay, yeah, of course, we can be.
Inequalities will fail.
No. D can be undefined for some programs. But the complexity is finite for every X, if it's universal. Because for every string, we can write some program which generates the string. So every string will have a finite description. So D is partial. Let's say it again. D is partial, but for universal D, the function KD is finite. Okay, we will have to make a break, but if you want to, let me say some questions, you can try to prove them during the break. So Kolmogorov complexity function is not computable. This is a bad news. But some kind of an unavoidable bad news. And for people who want a more difficult task, challenge, to think about, something to think about during the second part of the lecture, you can prove that for optimal D, every x has only constant bounded number of shortest descriptions. So, of course, it can happen that some string x has several descriptions of the same minimal length. Why not? There is some short description and some other short description of the same length and no shorter description. But so there is a statement you can think about, that the number of the shortest descriptions is always bounded by some constant which doesn't depend on x, but may depend on d. Or let's say it depends on d. Okay, let's make a break now.